Okay, so you did very well that you could plot phi distribution. Okay, now what we will do next is this. Okay, so I have shown you all this. So, but q square, x, and y in elasticity, all these things we will plot. Okay, so basically we will study the kinematic variables. Now, if you go to that folder, I have already saved kinematics.c, one macro. Okay. So you can open it. Okay. So as earlier also we did two methods, like directly energy information and theta information of the scattered electron, and also we have used the T Lorentz vector information. Okay. So here in this file I will show with the energy and theta information. You can do it later using T Lorentz vector. That is very easy. Okay. So exactly the same file which we have used it earlier. Okay, you can now recall. See, I have commented the 4 vector information. You can open and do it later. Okay. So what we did is the small q. What is small q? Yes. So that I had shown already to you. So you can make a 4 vector of this small q. Okay. And capital Q square formula you can see from the slides. Okay. So 4. So in electron energy means energy of the incoming electron. Okay. And energy of scattered electron is the, you understand from the name. Okay. And then it is sin squared theta by 2. That is the way I have written. Okay. So pau is basically is a function which we can use. So I have included C math in on top. If you want to use that, you have to include C math on top. Okay. Now you know the definition of this x. So you just write, you have done q square and then 2 star in proton star q. So here it is a dot product. Okay. And then y, that in elasticity also you have defined. Okay, so you have the basic information, then you take the like q square, x, y, you just calculate it. You have some experience of programming, this is as same like that. Okay, you develop your all these kinematic variables, and then you see, you now know how to fill in histogram, you have done for it phi, just the same thing I have did. So I showed you that why I have implemented 2 cuts, greater than energy should be greater than 6 and theta distribution should be less than 158. I have just put with that condition, I am writing my all the kinematics, let's say x, q square, y, and at the end you see I have filled 2 information, x and q square. So you, as far as you learned, so that is basically 1D histogram. So it is 2 information is filled, so it is basically 2D information, okay, 2D histogram you can say. For that, if you go on top of your macro, you can see I have defined TH2F, H8, okay, 2 variables. So in this case, you have to also give the range and also binning everything for 2 variables at the end. So in spite of 3 numbers, it will be 6. So along x-axis, if you see, the first number is x. So along x-axis, it is x, and y-axis is q square. Okay. So just remember, for x, I have used the binning size 10,000. Okay, I will tell you why I have done it. And for q square, I kept it 1000. Remember this number. Okay. And I have plotted, or you know already, it will be event by event. So entire loop, whatever events we have, we will go through it and fill all the variables information, x, q square, y, that we did. Okay, so here I forgot to tell you, initial information, incoming electron and incoming proton information, I have just defined like this. So electron is having your momentum or direction is along the z direction. Okay, so I have written px, py 0, pz. Okay, so these two combination will give you the basically your energy, center of mass energy around that. What is the number I took? 315, no? So that will get the center of mass energy of that. So I have written the proton also this. Okay, and you see this center of mass energy for this incident electron and proton is this. So you can, one thing you can do, so this is, but it is, you can include, it is not exactly, but it is such a high, means you can keep it is like a, like this one, okay. So it is 920 GeV and proton mass is what? 1 GeV. So you can include, but even you can exclude. So in the energy you can 921 you can write. Okay. So these two, this is your center of mass energy you are estimating. You can calculate what is that one, and this. Even any step when you are analyzing, if you want to see that what that value exactly is, you can do print it. The command is cout. Okay, so you do cout and see what is your in proton energy. Okay, everything you can just check. Okay, so I have filled up all this information. Now I will run it. Anywhere you have any question here before I run? Okay, so let me run first and then I will give you homework then, okay? See what are the things we have plotted? X, okay, you can't see anything here. Let's do the y-axis log. This is my x distribution. Let's go for y in elasticity. See, and then q square, momentum transfer. Okay, and this is my plot for going ahead for cross section or not, cross section and reduced cross section, all these things. So here, this 2D histogram, this is one of the important histogram for us. So along x-axis, x, along y-axis, q square. Okay, so what we have to do? Cross section, double differential cross section, d2 sigma by dx, dq square. Okay, so this is my base plot to go ahead with the cross section. Okay, so before I go move ahead, can you quickly just do y versus q square? From the same kinematics, just add one histogram, y in elasticity versus q square. Then I will go to this. Zero to one. So you have a freedom. You just check. I also don't know. Okay, you check. So you have x q square, 2D histogram, just follow that, okay? First define a 2D histogram, TH2F, okay? Then you fill y and q square, which you have already calculated, and then draw. Okay, good. Very good. So let's see whether I can also get that one or not. See? Okay. So we have to now move ahead. Okay, now we have did little bit of kinematic study, how it is changing x, q square, y, all these things we checked. Now we will go with that cross section. Okay. Now, so first, as I already explained to you, that you have x versus q square plot. Okay. So we have to just make a grid like of this. Okay. So it is 1 dx and dq square. And how many particles or electrons are there in that small grid? Okay. So we will do this. So that will give me d2n by dx dq square. Okay. So from the experiment. Okay. So now I will request you for another macro, which is basically your cross section versus x dot c. No, you are not able to do y. Just replace x by y. For the time being, it will be okay. Okay. So for this kinematics.c macro, you try with the Lorentz vector as well. That is homework. Okay. Now I am going for cross section. Is it visible? Okay. So what I did, I have already plotted x versus q square. Okay. In the earlier histogram, I have already plotted. So you can plot and go ahead with that. Okay. So here I have taken that histogram. I am not telling how to save that in a root file. Maybe later on I can tell you. Just for the time being, take that you have saved your information x and q square in a histogram. Okay. Now, what we will be doing, we will go for two for loop. We have two dimensional histogram. We for x and y, we will run two for loop. How do I go about it? So, for a particular q square range, this is my q square. I will take for a particular q square range, I will do what are the delta x. Okay. So for one delta q square and again another q square, what is the delta x? Okay. Like this, two for loops simultaneously will run. Okay. And if you recall, for q square, I have taken bin size 1000. I told you, at that time you remember that. For q square, I took 1000 and for X, I took 10,000. I told you that time, you should remember that number. Okay, so I will take a small width, that delta q square width and delta x width, and I will fill those information here. Okay, so here it is in little bit complicated way I did it. Okay, so basically if you just focus on this, how I am getting the q square. Okay, so histogram is H1, my q square information is on the y axis, and I am taking the, so it's a width. Okay, so I have a delta q square range. So I will take, to just mention it, I will take the mean value of that. Okay, the starting point of that q square, end point, and divided by 2. So that is the average. I will mention that delta q square width as the mean value. Okay, so that exactly I did with the first line. You see, I have taken this one. Okay, so if you remember your delta x versus q square plot, so I have chosen the bin in such a way that it will give you the range where you have the maximum statistics. I will show you that plot again. Yes. See, I cannot just blindly cannot take any range because there is a issue of the statistics. So I have chosen my range in such a way, you can see in this region, so that I get some entries in my histogram. If I take here or here, you can see I cannot go ahead with that. So I have chosen this region. If you see the bin's size or bin area, basically where you have a statistics. Okay, that's the reason I have taken a certain region. Okay. Okay. And here in the second line, which is delta q square, basically I have taken the what is the width of that delta q square. That you have seen this maximum and minimum, that one I have taken the difference. Okay. Okay, so this basically that 1000 I have taken. So here I just written in such a way that I can take the 4 q square ranges. I have calculated is 4 q square ranges. So if you see on scale q square, it is 10 I have written. So bin size is 10 into, if you are starting with 0, that means 10 into 1, 10 to 20. Okay, so this is the way of writing, nothing like that. So that later on, if I am going for another q square range, I just quickly go to the from 10 to maybe let's say 20. So I can switch. So like this, I have done for x as well. And then this line is the important line, which is this line is basically calculating for that particular dx and dq square, how many entries I have. See, I have used a function. This is my histogram, 2D histogram, H1, and then I am integral. Okay, I am integrating the entire information. So this is the minimum bin of x and the maximum bin of x for that delta x, and this is the minimum of q square and the maximum of q square. Okay, so I am defining that small box. I am telling and asking integrate all the entries. It will give me that number n. Okay. Similarly, now this is I am treating it as my data. So this data is the detected, the number of particles is detected by my detector. Okay, but I have to, as I told you already, when I am using detector, there is a detector efficiency involved. Okay, so I have to unbias my data. So I have to do my data efficiency acceptance correct. Okay, so that's why if you see, I have written here this efficiency. Although I am not doing, okay, we do not have that much time, and what I did, if you are efficiency acceptance for this calculation, you have to take help of the simulation, get that information and put it here. Okay, and dx dq square, already I told how to estimate that one. You have checked delta x delta q square. So that I already explained to you why you have to divide by delta x delta q square. Okay, so if you take larger, it will give you the more. Okay, so it should not depend on your width size. So you have to divide by that. Okay, now this I did, and there was another, if you remember the cross section, that formula which I have written. So I have done A into epsilon equal to 1, let's say for that, and delta x delta q square width I have already estimated and put it there. Okay, now remain is that L integrated luminosity. Okay, since integrated luminosity, if you are doing an experiment, actually you have to estimate what is your integrated luminosity. If you see any experimental paper, always there is written the root S is this with integrated luminosity of this much. Okay, so they estimate it. Okay, and then, but since we are taking the Pythia data, we will not go by any luminosity, but we will take the total number of events which we have generated. Okay, by that we will be dividing. Okay, so you got the idea. First you go plot x versus q square, then make it a like a grid, and for each grid you get what is the number, and then you do the efficiency acceptance corrected, divide by your delta x delta q square width, and also divide by the integrated luminosity. Okay, then it is your basically your data corrected, all correction you did. Okay, and that's give you the cross section. Okay, now here it is where I am saving this information. It is no more a histogram. I am doing a graph. Okay, so I will be have a 2D graph x. So there is a difference between graph and the histogram. Okay, I will not go in details, but there is a difference. So for x graph, when you are plotting, that is only 1 point. Okay, so each delta x and delta q square, I have 1 point. So now I am going to the graph. Okay, so you plot it, and for each I did it. So for 4 q square range, I have plotted this histogram. Okay, let's go for this. You can go very minutely what it is there in the cross section, but overall this is the idea. Now if I plot it, if I run it, see, so these are the 4 q square, how your cross section is changing with x. Okay, so don't go by the absolute numbers, because this is a just for learning. Okay, so I have taken Pythia data and I plotted how your cross section, double differential cross section for 4 different q square is changing with x. Okay, now what is our next step? So if you remember the flow, we have to go for reduced cross section, isn't it? From cross section to reduced cross section. Okay, so you know the relation between the cross section, I explained to you already. Okay, so you have cross section macro. Okay, and you know this sigma r equal to cross section into q to the power 4 x by 2 pi alpha square. Can you just try it? I will give you 2 minutes. Okay, you have to multiply your sigma by a factor, which is, you see how I explained to you now. This is your d2 sigma by dx dq square. If you take this factor which is outside this bracket to the left hand side, that become reduced cross section. So whatever the cross section macro I have given, you have to divide by this factor, whatever way you can. And you give me the graph of reduced cross section versus, don't be afraid, it's very simple. You whatever sigma you did, you have to do the multiply with that factor, it will give you sigma r. Just do it. Okay? If you can't, there is a rescue. Okay? Already that is there in your folder, I am not disclosing. First you try. How to get? Alpha value? Okay, I will give you. For the time being, I am giving you. So it is calculated already, you can put this one. Rest of the things are under control, you know. Q you know, X you know. What is there? 2 pi alpha square. Which one? In cross section macro. Yes. You know cross section, multiply that with this factor, it will give you the reduced cross section. Only one line. I will show you the formula. Yes. So q to the power 4 x by 2 pi alpha square into cross section. So I told you, no, power, that power. There is a function in math. So if you do, C math or that you have to include. So it is q to the power q square already is there. So only you have to square. Any of you? That I told you, given you. Okay. I will show you again. Yes. This I have written. Okay, you can, okay. If, okay, very good. Okay, so one of you have already done it. If you are not able to do it, so I have kept it in a junk.c. Actually, it is not junk. You just copy it to reduced cross-section.c. So there is exactly, you have to follow the same name. So there is, for this root file, if I open now, so you cannot give just arbitrary name. So if your macro name and this, it has to be exactly same. Okay. So if you are copying junk.c, so you copy to reduced cross.c. and then you try to run. Okay? Yes. Okay. Now, you have copied, you run it. Okay, I can move ahead. Okay. Now, if you see this formula, sigma r equal to F2 minus y square by capital Y plus and FL this. Okay. Now if I put small y equal to 0, then your FL is gone. You can get the F2. So you have calculated already sigma r, there you just put y equal to 0 and check. Okay. So if you see your folder, there you have one f2.c. So that I have done, but I don't think that you need to open that folder macro. You can do it from your function itself, from your macro itself. Just try it without seeing f2.c. Not coming? I said that whatever macro you are using, so if you see that if we want to go for F2, yes, so if you put y, small y equal to 0, that will give you F2. Okay, so reduced cross section become F2, isn't it? See the formula very carefully. Okay, so that you can do, or if you can't do it, there is already given macro F2.c that you can run. Okay. Okay. So don't go by the numbers. Okay, just at least see the tendency. Okay, Pythia doesn't have the proper cross section in it. Okay, so don't expect the proper numbers, but the tendency you can see with x along x-axis it is x, y-axis it is f2. Okay, so it is decreasing with x. Okay, so I hope you are able to do it this much. Okay, now we will go for the FL. Okay, longitudinal structure function. So I said for that we need to go for the two energies. Okay, so I have, if you see that folder, I have two root file. One is at center of mass energy 225 GeV, another is 318 GeV. Actually, it is the data also, this H1 HERA is having analysis in these two energies. Okay, so that's why I have taken these two energies. So, if you remember what I have explained to you in the slide, so this is the way, isn't it? This is the slope, sigma reduced cross section for one energy minus reduced cross section of the second energy at y1 and y2, but same x and q square. Sigma FL at x q square. So for both the energy or y1 and y2 root s, you have to take the same x and q square. Okay, and you also estimate the denominator, y small to this small y2 square by capital Y2 minus y1 square by capital Y1. Okay. Okay, so it became, now you have to handle two things. One is for one energy, another is for no. So I have given you another macro. So that FL structure function dot C. Okay. So now you see, I am reading two files. Okay, one is 318 GB, another is 225 GB, and all this calculation I am doing for both. Okay, everything we have to do for simultaneously for both the energies. Okay, so one will give you reduced sigma 1, another will give you reduced sigma 2. You have done reduced 1, you just do it for 2. Okay, and I have defined exactly the numerator and denominator separately, then I have divided. Okay, you can see this. If you want to check your second energy, that reduced cross section, you don't have to do anything. Just in this graph, in place of FL, you just put reduced sigma 2. It will give you. Okay, the graph automatically adjusts all your ranges, everything. You like histogram, you give range. No, what is the from this to this, that graph you don't. You just change it, it will automatically adjust. Okay, so you do it or for all 4 q square and run it. But don't go by these numbers. Okay, it's very. So why this kind of, you can see this 0 is coming here. Basically, you do not have data there. Okay, so it's you should not trust your all these no points. Okay, you have to very carefully. You have to interpret and see those data. Okay. Now, so that's not all about the analysis. The main part is remaining actually that you have to do for error analysis. Okay, otherwise this number doesn't make sense any. Okay, so that takes for us like systematic errors. It takes, even if you have everything, no, for all the checks and everything, minimum 1 semester. So it's 1 hour job. It's not a 1 hour job. Okay, data analysis. Just I wanted to give you a flavor of how to do the data analysis. Okay, now all of you have done it. Okay, now we have still 15 minutes. Can you do the same job? Reduced cross section, how it is changing with Y. Okay, just try to do it. If you can do it, that means you know little bit of data analysis. Just do it. Okay, you have everything. Just do the reduced cross section, how it is changing for different q square, how it is changing with Y. I have shown you for 4q square, how it is changing with X. Just do it with Y. Y is the inelasticity. Yes. So you do it like this. So data analysis looks easy, no? Huh? It will be same, na? Dx, you have to plot first q square versus y. And then you y. So even if it is not reduced cross section, at least cross section, okay? You have, everything is there. You have to do little bit changes and then. So for x versus q square, I have saved that root file histogram in a root file, but it is not saved in that root file, okay? So first you have to generate that histogram, y versus q square. Save that information, then you do this study, okay, which is there in the cross section macro. Yes? Yes. So junk.c you have to copy to reduce, that's what I explained. It will not run. So you have to first copy it in the, open that file and see on top what is written. So exactly the macro name should be that, then only it will run. See here, you have to name the same as then only it will run. So copy it into that name. So how do you do it? Y versus Q square. Try? Okay. Any idea? Or you have started already? So you have already plotted, no? F2, sorry, Q square versus Y. Remember? So that two way you can do. The same, you just do it in the cross section macro, and then you fetch your that histogram, y versus q square. That is one idea. Another is you run the kinematics and save that histogram in a root file, and then you put that root file in the cross section macro. Two way you can do. Okay. So I will show you one method and then I will stop. Okay. So you have to, if you see the kinematics, if you want to save in a root file first, you are creating a root file. Okay, earlier you have read. I saved the information as a data and then you read that data. Okay, now you have to create a root file. In that you have to save your y versus q square plot. Okay, so I have defined. So you see the difference between the previous one and this one. Here I am recreate. I want to create a root file. Okay, which I am given some new name and file 4. Now you write those information in that file. Okay, and then you close that file. I may be wrong here. It may not be inside the loop. It should be outside the loop. Just I forgot. Just I have to check. Once check. Okay. So this is one idea. Save your root file histogram in a root file, and then exactly the way I have done your x versus q square, you do that. Okay. Or otherwise, in the same macro, you plot. Okay, so this is your homework. So tomorrow you tell me whether you have done it or not. Okay, I have shown the reduced cross section and the, F2 and FL. You have to show me sigma reduced cross section versus Y. That is your homework. Okay, with this I will close.